Uh, Hello everyone, my name is Kenji Michimata. Today, I'd like to present our result on heterogeneous integration of an indium arsenide nanowire with energy-efficient CMOS delta sigma modulator. First, let me show you the outline of my presentation. I'll start off with the introduction, including background and approach. Next, I'll explain our experimental method for indium arsenide nanowire on CMOS substrate. Then I talk about the measurement results we obtained from fabricated chip, in particular DC and noise shaping characteristics. Finally, I'll conclude my presentation. Now, I'll begin with the introduction. Nanowires and nanotubes are materials of interest in sensor applications because of their possible ultra-high sensitivity due to the high surface-to-volume ratio. Moreover, integrating these materials onto a CMOS substrate is desirable for low-power sense applications. Conventional approaches are mostly on carbon nanotubes with simple CMOS circuit. For example, C.L. Chen and his co-workers have demonstrated a single-wall carbon nanotube on CMOS substrate. Then we use carbon nanotubes as a feedback element of the operation amplifier, like this figure. This slide shows our approach. We try to integrate indium arsenide nanowires with energy-efficient inverter-based delta sigma modulator. Indium arsenide is known to have a native surface inversion layer with high electron density. So we can expect the resistance is highly sensitive to surface absorption. And delta sigma modulator is essential circuit in high resolution analog to digital converters. From now, I talk about experimental method for indium arsenide nanowire on CMOS substrate. This and next slide shows growth and fabrication process of our indium arsenide nanowire CMOS circuit. First, we grew indium arsenide nanowires on gallium arsenide 111B substrate by using vapor liquid solid mode or metal organic vapor phase epitaxy. The growth time and temperatures are 30 minutes and 460 degrees centigrade respectively. Then we use gold nanoparticles as growth seeds, and we also use 3-methyl indium and tertiary butyl arsines as precursors. In this growth method, we obtain indium arsenide nanowires that has a length and diameter of approximately 20 micrometer and 50 nanometer respectively. After the growth, we dip the substrate into the isopropanol and mechanically remove the nanowires there. Then, we carried out nanowire deposition by field-assisted self-assembly (FASA) process. We dropped isopropanol droplets containing indium arsenide nanowires onto CMOS substrate, and then collected them on the gap between the FASA electrodes by dielectrophoretic force. The nanowire and the CMOS circuit was connected to each other by these FASA electrodes. During the FASA process, we applied an AC voltage as low as 1.5 volt peak to avoid introducing any damages to CMOS circuit. Now I'll explain our indium arsenide nanowire CMOS circuit. We designed the circuit consisted of voltage divider using series connected resistors and delta sigma modulator. Then a single indium arsenide nanowire is used here as one of the resistors. The delta sigma modulator converts voltage across the nanowire into density-modulated digital pulses like this. This slide shows our second-order inverter-based delta sigma modulator circuit. This circuit was fabricated by a standard 0.18 micrometer CMOS technology. As I explained previously, to obtain high efficiency, we use a Class C inverter-based delta sigma modulators here. From now, I talk about the measurement result we obtained from fabricated chip. This is a photograph of fabricated chip consisting of delta sigma modulator and nanowire resistor. And this same micrograph shows nanowires we deposited between the FASA electrodes. This slide shows typical output waveforms obtained from the chip after the indium arsenide nanowire deposition. The top waveform is for an input voltage of 1 volt, and bottom one is for an input voltage of 0 volt. As you can see, the pulse density is higher for high input voltage than for low input voltage. In this matter, the analog input was converted into density-modulated digital pulses. And in other words, the duty ratio is higher for high input voltage. This slide shows the duty ratios of delta sigma modulator output as function of input voltage. The duty ratio obtained from the chip with the nanowire is about two-thirds that observed for the chip without nanowire, because input voltage was divided by resistors R1 and R nanowire. This was confirmed by the fact R nanowire is approximately 200 kilo ohm, being almost the same as that of R1. The nonlinearity behavior earned here is probably due to nanowire itself and contact resistance to connecting electrodes, because a similar nonlinearity behavior were observed in V nanowire graph reproduced from separate IV measurement of an indium arsenide nanowire only. This proves the nanowire resistance can be sensed and converted digital output. This slide shows noise shaping characteristics. The SNR are 57.0 dB after the FASA process. This is comparable to the value before the FASA process. This value corresponds to around 10-bit resolution, which suggests that we can tell the nanowire variation of indium arsenide nanowires with in 10-bit accuracy, or 0.1%. In conclusion, we've demonstrated the nanowire-CMOS heterogeneously integrated circuit by using FASA process. We've observed the successful operation of indium arsenide nanowire inverter-based delta sigma modulator circuit. And these results suggest that variations in the nanowire resistance caused by chemical absorption on the nanowire surface can be sensed and converted into digital output. Thank you for your kind attention.